Okay, welcome back everyone. So this is the last week of class. The second midterm / homework 6 should have been posted yesterday. You all have access to it, and it's due at 4 o'clock on Friday. Okay, so this is the last week of all homeworks, exams, and class. And this is probably my favorite topic that we're going to cover this week, which is data analysis and the singular value decomposition. So this is just kind of a tiny peek into the wide world of data analysis, but I want to tell you about some of my favorite methods and some of the really powerful things you can do with very, very simple mathematical tools. Okay? So today we're going to talk about the singular value decomposition. The SVD. So the SVD is probably so if not the most important algorithm of the last 100 years, it's maybe the second most important algorithm after the fast Fourier transform. And this is revolutionizing how we deal with large data sets. This is really the basis for how Google determines which pages to rank first, how Amazon determines which products they think you're going to buy, how Netflix builds a profile of what movie taste you have, and the list goes on and on and on. Okay, so especially in Seattle and San Francisco and New York City, the singular value decomposition is becoming the most important algorithm for making tons of money after grad school. Okay? So SVD is awesome. It's a very, very, very simple matrix decomposition. Okay, so it's a matrix decomposition. And it's a very useful matrix decomposition. Okay, so how many of you have heard of the SVD before in some other context? Okay, good. So some of you have heard of it. So the singular value decomposition, we're going to be able to do things like build facial recognition software. Okay, so that's something that I'll do on Friday. We can start to look at the genetic markers that are characteristic of healthy versus sick patients. So one of the examples we'll do probably tomorrow or Wednesday is look at the genes for ovarian cancer and try to determine which genes are or are not responsible for ovarian cancer. It turns out that the singular value decomposition is very useful for that. We can also do more pragmatic things like, well, that's pretty pragmatic, but more simple things like figure out what factors affect housing prices, what mixture of various parts will determine the heat production from a cement mixture. I mean, the list goes on and on and on. The singular value decomposition allows you to take training data from your past experience and essentially build a model and extrapolate what other situations would look like. Okay? So this is the basis for machine learning, which a lot of you are going to be bringing into your research in the next years and years. Okay? Even if you don't know it yet, machine learning is going to play a part in a lot of your lives. Okay, good. So the idea is that the singular value decomposition is particularly useful when you have big data. Okay, so good for big data. And everybody has a different definition of what big data means. My definition of big data is relatively all-encompassing. So big data is data that's bigger than what I can plot in 3D. Okay, so 5D data is bigger than 3D. But oftentimes big data would be like the results from a huge fluid simulation that Boeing might run, or the results from a huge questionnaire. Okay, so the post office for I guess decades and decades now has been giving this gigantic psychological evaluation to every single person who applies for and enters the postal service. So they have millions of employees answering hundreds of questions. And if you write down all of the multiple choice answers in a big matrix, you have a gigantic data matrix. Okay, so questionnaires, fluid data, experiments. If you wanted to measure the seismic data on planet Earth, or the position of all of the stars, or how every senator has voted, right? These are examples of big data. And the singular value decomposition is a way of extracting the most important features. So we want to know what are the most important features in the data set. Sometimes you call these dominant features. And what it means for a feature to be dominant or most important is that it comes up again and again. These are features in your data that you see over and over again, so they're strongly correlated. Okay, so let's do some examples of the singular value decomposition and start getting a feeling for what this thing actually looks like. Okay, so let's say that I have a data matrix X. And typically what I'm going to do is I'm going to write this as a bunch of column vectors x1, x2, x3, dot, 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 xm. Okay, so X is an n by m matrix. Okay, please interrupt with questions at any time if I start getting confusing or unclear, because I deal with the SVD like every day, and it might be easy for me to go into something that I know that you don't. Okay, so each column of this data matrix X represents some big measurement. Okay, so this big measurement could be this could be the temperature measurement at all of the weather stations on planet Earth on day 1. And this would be the temperature measurement at all of the weather stations on planet Earth on day 2, day 3, dot, 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 up to day m. Okay? So each column is a high-dimensional measurement. Measurement vector. Okay? Another example is, let's say that I have a fluid simulation for flow past a cylinder or a volcano or something. I could take the fluid velocity field at all million grid points and stack them in a really, really, really tall million by 1 vector. Okay, and this would be the fluid velocity at time 1, time 2, time 3, dot, 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 up to time n. So each column is a very high dimensional measurement. The dimension of the measurement is how many pieces of information I need in that measurement. And I have m examples of these measurements. Okay, and so the m examples might be a sequence of measurements in time. So often a sequence in time. And if they're a sequence in time, then we call them snapshots. Makes sense, right? You have, you kind of imagining you're taking data with your camera, and at every moment in time, you take a snapshot. These are each snapshots of data. Okay? So does it make sense how we're gathering this data? Another example, I'm just going to keep giving you examples of data matrices that have come up in my research or in my collaborators' research. So this is a good example. Another example, you might take the number of infected people infected with polio in every single district of Nigeria. So this might be 400 or 500 districts in Nigeria, and every number in that vector would be how many cases of polio you've had that month. And each of these snapshots would be that tally for that month, month 1, month 2, month 3, and so on and so forth. Okay? And so what we want to do is we want to find examples of things like, are there correlations between these snapshots? Are there places in Nigeria that are just more prone to having outbreaks of polio? Okay, so we want to be able to find dominant features in this data set in a way that we can actually understand what we're looking at. Okay? So the singular value decomposition is a way of rewriting our matrix X in the following way. So we take our big data matrix X, and we write it as the product of 3 new matrices. We say that it's equal to U times sigma times V star, and star just equals complex conjugate transpose. So technically, the singular value decomposition exists for complex data matrices X. Like if you had the columns of X came from a Schrodinger's equation simulation, then those might be complex valued. And in which case, V would not just be the transpose, but it would be the complex conjugate transpose. We are only going to deal with real value data in this class, and so star to all of us should mean transpose. Just matrix transpose, super simple, okay? So we're taking our matrix X and we're rewriting it as the product of three new matrices, U, sigma, and V. And it turns out that these new matrices are actually much, much simpler and better organized than our original matrix, and we can use these for tons of things. Okay, so I'm going to tell you what the properties of U, sigma, and V are. I'll tell you why they're important, and then I'll give you an example. Okay, so U is an n by n square matrix. Sigma is an n by m diagonal matrix. What do I mean by a diagonal matrix? Just numbers on the diagonal. They're very closely related to eigenvalues. So everything off the diagonal is equal to 0. And V is an m by m square matrix. Okay, so in the example that we were looking at over here, if this is the number of people with disease in different districts of Nigeria, or this is the fluid velocity at all million grid points, or this is all of the weather stations on planet Earth, oftentimes our size of our column, n, is much, much larger than the number of snapshots we have, m. Okay, so for some examples, for many examples, we have n is a lot bigger than m. So examples of that would be like disease modeling, disease, weather, fluid modeling, and so on and so forth. There are a few examples where m is a lot bigger than n. Any ideas what some examples would be? Yeah, the survey is a great example. Or m might be much bigger than n. This would be the survey. What's some other good example? Sometimes I put electrodes, sometimes people I know put electrodes in brains, and they might measure 10 different electrode signals, but they would measure them at 10 kilohertz. Okay, so they'd have 10 measurements a bajillion times. Okay, so like brain measurements. Another example would be the stock market. So even though there are tons of stocks, there's not that many, it might be hundreds or thousands, but I have the stock ticker for every second for the last 50 years. Okay, so I have more snapshots than I have number of stocks. And this is a great example. The stock market is one of the most interesting data sets to analyze with these methods. And so that's why New York City is in the list of people that are benefiting tremendously from the SVD. Okay, good. So in a lot of cases that I work with, U is a gigantic square matrix, V is a smaller square matrix, and sigma is a diagonal matrix that's the same size as X. Okay? Now, the last thing I'll tell you about U and V is that U and V are extremely special matrices called unitary matrices. This probably deserves red. So U and V are unitary. Unitary. So how many of you have heard of unitary before? Okay. Unitary matrices are some of the most special matrices on planet Earth. They're amazing matrices that have this great property that U times U star is equal to U star times U, and that's both of those are equal to the identity matrix, the n by n identity. And the same thing with V and V star. So V star equals V star V equals my M by M identity. So these are extremely, extremely special matrices, U and V, such that if I want to take the inverse of U or the inverse of V, all I have to do is complex conjugate transpose it. Why would that be a really useful property for a matrix to have? That it's easy, that its inverse is the transpose.
Makes it commutative.
It makes it commutative. What's maybe a more practical day-to-day reason? It's easy to compute. So if I wanted to invert a generic n by n matrix, how expensive is that? Order n cubed. Okay? If I want to invert a unitary matrix, I just multiply by its transpose. That's order n squared. Okay, so it's way, 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 way easier to matrix inverse unitary matrices. And they also have beautiful geometric properties and all kinds of other things. So they preserve distances. If I take two vectors x and y and I map them through a unitary matrix, their angle and lengths are preserved. That's a pretty special relationship. Only unitary matrices have that property. Okay, so if I take any vectors, any pair of vectors, and I map them through U or I map them through V, their lengths and angles between them are preserved. Super duper simple and super powerful. So the singular value decomposition, the last thing I should tell you is that this exists and it's unique for all matrices X. And these could be complex matrices, so all complex n by m matrices. And I'm not going to prove this. If you want to prove it, you can. It's in books. You can Google it. It's really easy to find a very, very simple proof for why this is true. But this definitely exists, and it is unique for every possible matrix. So any matrix you can name, X, I can give you a U, a sigma, and a V, such that this product equals your matrix, and we have these properties. Okay? Okay, so is everyone with me so far? We have a big data matrix X. It holds lots of information that I care about, and I want to extract the patterns in this data that are the most useful for informing policy or design or making money or selling products or whatever you want to do. We want to find what the most important features of this data are. Okay, so the last piece, I'm going to keep saying the last piece. There's just more and more pieces of this that keep coming. So another piece of information about the singular value decomposition, probably one of the most important parts, is that this sigma matrix is a diagonal. I'm going to draw this for n larger than m. Is a diagonal matrix with what are called singular values on the diagonal and zeros everywhere else. So sigmas on diagonal, these are called singular values. The reason they're called singular values is completely historical. Like 100 years ago, people looked at singular integrals and found out that you can derive this singular value decomposition, and that's not at all how we derive it now. But they're still called singular values. And they have the really, really important property that sigma 1 is bigger than or equal to sigma 2 is bigger than or equal to sigma 3 all the way down to sigma n, m. And they're all either greater than or equal to 0. They're all positive, or they're all non-negative. And they're in descending order from biggest to smallest. And so this allows me to do something really, really interesting, which is, so I'm just going to write this out explicitly. We have our data matrix X equals U1, U2, dot, 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 UN, the columns of my U matrix, right? Times sigma 1, sigma 2, dot, 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 to sigma m, zeros everywhere else, times V1, V2, up to Vm, complex conjugate transpose. Okay? This is just what the singular value decomposition looks like. But the fact that my sigma matrix in the middle is purely diagonal with zeros everywhere else means that what this is really equal to is sigma 1 times U1 V1 star plus sigma 2 U2 V2 star plus sigma 3 U3 V3 star plus dot, dot, dot. Okay, does this, maybe I should be explicit about why this is true. So let's take this matrix times sigma. So take V star times sigma. So I get essentially my V1, this whole thing is transposed, so it should really look like this. It should look like V1, V2, dot, 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 Vm star, right? And so what this sigma 1 in the first diagonal does is it just pulls out the first row of V and the first column of U, and everything else is multiplied by zeros. Make sense? Yeah? The second singular value only multiplies the second row of V and the second column of U, and so on and so forth. And so what this does is it breaks my matrix X down into the sum of m rank 1 matrices. Each of these is a matrix. So this is a sum of m rank 1 matrices. Does everyone know how to, yeah?
So here the star and the V's, it's just the complex conjugate because they're already transposed, right?
It means complex conjugate transpose. So I mean U is a column vector and V is a row vector. So this leads into my next question. So what does it mean to take a row vector times a column vector times a row vector? So we know what we get if we take, let's say that I take a row vector 1, 2, 3 times a column vector 4, 5, 6. We know how to do this, right? It's just 1 times 4 plus 2 times 5 plus 3 times 6. Okay? But what if I do it the other way? What if I have a column vector times a row vector? How do I do that? So the other one is called the inner product. This is called the outer product. And think about this as like U1, and think of this as V1 star. Right? If V1 is real valued, then I just take a column and I turn it into a row. That's V1 star. So the way that I compute this inner product, first of all, it's going to be a 3 by 3 matrix. And these have the same inner dimension. Okay? They're both 1 on the inner. So I take 4 times this whole row vector, 4, 8, 12. Then I take 5 by this whole row vector, 5, 10, 15. And then I take 6 by this whole row vector, 6, 12, 18. So this is U1, V1 star. It's a matrix. Okay? So U1, V1 star is a matrix. And it's a rank 1 matrix. And what do I mean by rank 1 matrix? all of its columns are linearly dependent on the first one, and all of its rows are linearly dependent on the first one. So if I looked at this matrix, I would say that the columns of this matrix only span one direction, or the rows of this matrix only span one direction. They don't span all of 3 space. They only span one dimension. So this is a single rank 1 matrix. Okay. So writing this as U times a diagonal sigma times a V star allows me to take my matrix X and write it in a series of rank 1 matrices. This is a matrix plus a matrix plus a matrix, dot, dot, dot. And since sigmas are in order of importance, each of these matrices is in order of importance. This first matrix is the most dominant contributing factor to the data in X. And the second matrix, sigma 2, U2, V2 star, is the second most dominant contributing factor to the matrix X. And then the third and the fourth and the fifth. So does that make sense so far? Do you have a question?
Yeah.
Okay.
Just how do you develop that sigma matrix?
So this sigma matrix, I'll show you kind of where it comes from. But for now, we just take for granted that it does exist and that we can write it in an ordered sigma 1 to sigma m. Yeah.
In this case, it looks like you have m smaller than n, but if it was the other way, the zeros, instead of being below, would be to the right.
Exactly. So if m, yeah, exactly. If this was like so I call them tall, skinny matrices or short, fat matrices. And for a tall, skinny matrix, the zeros are below. For a short, fat matrix, the zeros are on the right. Yeah, exactly. But you have the same sum of rank 1 matrices. This is called a dyadic sum if you're interested. Sounds druidic, dyadic sum. Because these are dyads, U1 and V1, they're dyads. And because U and V are unitary, what it tells me is that the columns of U are orthogonal to each other. U1 is orthogonal to U2, it's orthogonal to U3, because otherwise I wouldn't be able to get this identity. Same thing with the columns of V, they're all orthogonal. Okay, so these rank 1 matrices also span orthogonal directions. So when I add them up, I build more and more rank into my matrix X. Okay, we're ready for the final piece, and then I'm going to show you a matrix example. So the actual final piece, I hope this is the final piece, is that you can use this to approximate a matrix. Useful for matrix approximation. So what do I mean by matrix approximation? How would I make this useful for matrix approximation? So I've written my matrix X as a sum of a bunch of rank 1 matrices. I could always just truncate that sum after the first couple. Right? I could just say, well, X is approximately equal to U1, U2, U3 times sigma 1, sigma 2, sigma 3 times, V1, V2, V3 star. I can say that my matrix X is approximately equal to just the first 3 of those matrices in my sum. Because I know that sigma 1 is bigger than sigma 2, is bigger than sigma 3. So all of the stuff I'm throwing away is small in some sense. It's, sigma 4 is smaller than sigma 3, sigma 2, and sigma 1. So the stuff that I'm throwing away are all smaller than the things that I'm keeping. Okay? So this is the idea here. The reason that this is so important is that at any point that I decide to truncate, I'm guaranteed to have the best possible rank 3 approximation to my matrix at that level of truncation. So if I only keep the first 3 modes and the first 3 singular values, these are guaranteed to be the best 3 possible features in my data that capture the most information in this data. There's no other 3 U's, sigmas, and v's that will better approximate this matrix X. And if I wanted to keep 5 pieces of information, I would keep, U4, U5, V4, V5, and sigma 4, sigma 5. If I wanted to keep 9, I would just keep 9. I can keep as many as I like and throw away as many as I like, and I'm guaranteed that that's the best approximation with that much information possible. Okay, so each of these columns, U1, is more important than U2. That's more important than U3. That's more important than U4. Similarly with V1, V1's more important than V2, than V3, than V4. They're hierarchically ordered in importance of how much they explain your data X. And the great thing about these features is that they have the same shape as my measurements. My U's are exactly the same shape as my X's. So for example, if X were a bunch of columns of ovarian cancer data, like all of your gene expressions, U1 would be the most important genes that express ovarian cancer. U2 would be the second most important linear combination of genes that expresses ovarian cancer. Similarly for disease data, a column of X might have been the disease populations in each of 500 districts in Nigeria. So U1 is the most important mixture or ratio of diseases in those districts. U2 is the second most important that explains my data that I've collected. Okay, same with stock market, same with everything else. If my data was collected in time, so X1 was at day 1, X2 was day 2, XM was day M, then these rows of V correspond to time histories. Okay, these are the dominant time patterns. So for example, if I take the stock market data and I run it through the singular value decomposition, there's 2 dominant modes that I see over the last 10 years. Any guesses what the dominant modes are for the stock market in the last 10 years? What happened in the last 10 years? So there was a huge crash in the stock market in late 2008. I was sitting in a BMW dealership getting ready to test drive a car I couldn't afford at all when I saw on the news that the stock market had crashed. Okay, so the first actual dominant mode is growth. The first dominant mode in the stock market, even with the crash, is growth. And the second dominant mode is a huge crash and recovery. Okay? These are my V modes, because those are the time progression. This is the dominant time progression of all of my U's, or at least of U1 and U2. Okay, so these are extremely interpretable quantities. The columns of U are like my measurements. They're the most dominant linear combination of measurements that show up in my data. And columns of V, or rows of V star, are the time histories of those measurements, the dominant time histories that I see over and over again. So for example, in the disease, you see a dominant 1-year cycle, because there is a 1-year, cycle where people spread diseases more regularly. Okay, questions before we go on to some MATLAB and some real, actual examples? Yeah?
So if sigmas are ordered in rank of value, like I said earlier, how are those developed?
How do you actually compute these things?
Yeah, or do they correlate to your rows?
Okay, good. So first of all, I'll just say I just wrote a book chapter on the singular value decomposition, and I'm going to post sections of it on the website. If any of you want all of it, you can email me. And everything I'm going to derive here is fleshed out a lot more detail in here. But the basic idea, I told you that the singular value decomposition is measuring correlation between rows and columns of X. Okay? So my U structures, the U matrix, is ordered. And each column of U is a dominant correlation between columns of X. Okay, so this measures correlation among columns of X, and it does it in the following way. So if I want to measure correlation among columns of X, what I'm going to do is I'm going to take X transpose, star is just a fancy transpose, just the transpose, times X. What is the size of X star X? Sorry? Well, I take this tall, skinny matrix that's n by m, and I knock it on its side. So now it's m by n. And then I multiply it by the tall, skinny matrix n by m. So this is an m by m matrix. And it's a matrix of inner products. This is a big matrix, m by m, of x1 transpose x1 times x2 transpose x1, I think, x3 transpose x1, dot, 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 x1 transpose x2, x2 transpose x2, dot, 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 dot. Okay? I literally just take every column of X and I inner product it with every other column of X, and I build out this huge matrix of inner products. Okay? And if some of these columns are really correlated with each other, then what should their inner products look like? They're going to be very large, right? So columns that are correlated give large inner products. Columns that are decorrelated give small inner products. And so the idea is that, let me make sure that I get the math right. So the idea is that X star X times V equals V sigma squared. And we also have that X star times U equals U sigma squared. And I'm going to call this sigma A and sigma B. They're slightly different than the real sigmas that we wrote down. So the idea is that this is an eigendecomposition. Okay, X star X is a big matrix. X star is another big matrix. V are eigenvectors of X star X. And sigma is a diagonal matrix of eigenvalues. Similarly for X star, which is a much bigger, maybe a million by million matrix, U are the eigenvectors, and sigmas are the diagonal of eigenvalues. Okay? So V are, eigenvectors, and sigma squared are E values, and similarly here. And so this one is going to be an m by m matrix of eigenvalues on the diagonal, and you just take those m by m eigenvalues, take the square roots, and those are my sigmas. So that's basically the answer, is that I take X star X and I do a huge eigenvalue decomposition. I get the eigenvectors, and then I get the eigenvalues as the diagonal elements of this matrix, and those are my singular values. So my singular values are the square roots of the eigenvalues of this matrix. This matrix will have a million or a ton of eigenvalues, but most of them are going to be 0. It just has to be. You can prove it. Unless I had a million snapshots, in which case then I could have a million real eigenvalues. Okay, so this is how you would actually possibly compute it by hand. There are much better ways to compute this in a computer. But this is the conceptual way that you would actually get it. I would take these huge correlation matrices. I do an eigendecomposition, and I would get U and V and sigma. Yeah?
So that sigma A and sigma B are slightly different from one another?
They're just different in the size. So sigma A is an m by m. Sigma B is an n by n. They have exactly the same non-zero eigenvalues. These are all things you can prove and demonstrate if you want. Okay, so there's lots more I can tell you about the singular value decomposition. For example, I would never actually compute it this way. There's lots of better ways to compute it, and I'll show you that on Wednesday, but I want to give you an example. So in this example, what I'm going to do, this is kind of a simple example. What I'm going to do is I'm just going to take a matrix. So a really easy example of a matrix is an image. Right? An image is a matrix. So I'm going to take X equals an image of my dog. His name is Mort. He's Amish. Okay? So this is going to be an image of my dog, Mort. He's going to have something like 1,000 by 1,000 pixels. And what we're going to see is that lots of his column vectors are correlated, right? Because he has correlated features, right? If you look at one column, it looks like the next column. And lots of his rows are also correlated. So I can apply the singular value decomposition to approximate my dog Mort with a much lower rank matrix, and I can do image compression in this way. So I can say that this really equals some U sub R, sigma sub R, V sub R transpose, where I just keep the first R columns. Instead of the first 1,000 columns, maybe I'll keep the first 50 columns, the first 50 singular values. And I'll get a big compression, like a factor of 20 compression. Okay? Any questions while we code this up? Okay, this is Mort. And, okay. So we all know how to read in images now. We're going to load dog into a matrix A. I'm going to convert that matrix A into a grayscale, just numerical values, into the matrix X. So X is my data matrix. And then I'm going to do the SVD. So in MATLAB, the SVD is beautifully simple. It's one line. U, comma S, comma V equals SVD of X. So S is just sigma, because I don't like typing sigma. Okay? And I'm going to plot my original dog. And then what I'm going to do is for R equals 5, 20, and 100, I'm going to create an approximate Mort with the first 5 columns of U times the first 5 singular values times the first 5 columns of V star. And then I'll do that for 20 and 100. Make sense? So these are rank 5, rank 20, and rank 100 matrix approximations to Mort. Takes a little while to do the SVD because Mort's a large file. And so this is what we have. The original dog in the upper left, pretty crisp and clear. If I only keep 5 modes, which is 0.58% of the original data storage, so this is about a 200 times compression, it's a really crummy dog. Terrible, right? Like you can kind of almost convince yourself that there's nose, eyes, and ears, but that's a stretch. When I keep 2.3%, it looks like a grainy dog. You can see some of his features. You definitely know it's a dog, but you can't tell everything about him. But then when I start to keep more like 100 features, you actually get a lot more resolution in the image. It's a little hard to see here. It's not perfect, but you do see a lot of the features. You see like flecks of snow and things like that. You get whiskers with 100 modes. Okay? So even complicated matrices can be approximated by much lower rank matrices using the singular value decomposition. I wouldn't really recommend the SVD for image compression. I'm just showing you this as an example that illustrates the concept of low rank matrix approximations. Really, we would do the fast Fourier transform and do FFT image compression. It would be way, way better. Okay, questions about this figure? Yes?
How do you get like each individual pixel? How does that correlate from one to the next?
So this is completely looking at correlations in the columns and correlations in the rows. And you can kind of convince yourself that this makes sense. Because let's say I take a column right here in the dog's midsection where it's like white, brown, some stuff, white. Well, if I look just one row to the right, or sorry, one column to the right or one column to the left, those are going to have big inner products with each other, because the column to the right and the column to the left are also going to have a lot of white, then brown, then white, then brown, then white, then, they're going to basically look the same. So there is a lot of correlation in neighboring columns and neighboring rows. And if you look at the 5 most dominant correlations, you actually see those patterns popping up. I see white, brown, white, not quite as brown, white. Right? Like that is one feature that's creating that entire back midsection. And you also have a pretty simple, white, dark feature. Okay? So this really is, there are 5 rows and 5 columns, and you're taking linear combinations of those to build up this mort. That's why it looks kind of crummy. So another thing you can do is make this plot of the singular values. So I should probably actually just do this. So I could plot on a semi-log y. Semi-log y is just log in the y direction. So I'm going to semi-log y the diagonal entries of S. Okay, these are my singular values. Maybe I should make them... Okay. So what I find is that my first singular value is really, really large, 10 to the 5. That's 100,000. The next one is a lot smaller, 10 to the 4. So the first singular value is 10 times bigger than the second one. The next one is smaller, smaller, smaller. So they are ordered from smallest to biggest. And then eventually they get much, much smaller compared with this original one. Okay? Oftentimes you'll want to plot the cumulative sum. So you do the cumulative sum of the diagonal entries divided by the sum. And what you can find is this plot on the right, which shows you, for example, the first mode, the first column of U and the first column of V account for 28% of the information in the dog. 28% of the raw information content of that image is in the first column of U in the first row. And then if I had 2 rows and 2 columns, I would get 34%. If I had 3, I would get 38. 5 gets me 42.46% of the total information. 42 is not enough. That's why it looks crappy. But if I go up to 100, I see that I'm actually getting about 75% of the energy in the dog. And it just keeps getting better and better and better and better. The more modes, the more columns I include, the better my mort approximation gets until I get to 100% mort. Any questions about this? Does it make sense what we're doing? Now, this was a single image where we're looking at correlations between his rows and columns. We could also put in many images that have been reshaped into extraordinarily large column vectors. So that's something we'll do. So I could take a picture of every single one of your faces, and I could create a big column vector with 1,000,000 pixels for each one of you. And I could have each of those as my columns of X. And then I could do the same analysis, and I could find the dominant facial patterns that are shared between all of you, the dominant facial correlations from everyone in the class. Or I could take 100 pictures of just one of you in different, like expressions, happy, sad, angry, and I could find your individual dominant facial features. Okay, so that's what we're going to do on Friday. That's called eigenfaces. This is an eigen-based method, eigendecomposition, and so those are eigenfaces. And that's the basis for Facebook facial recognition and all the scary stuff that robots are going to do in the future. It's pretty cool stuff. So I told you a lot about the singular value decomposition today. You can read more about it. I'm going to post the first section tonight. On Wednesday, we're going to talk about more about the correlations and some real practical examples like ovarian cancer. And on Friday, we're going to look at eigenfaces, and we're going to build our own facial recognition software. Okay? All right, thank you.